The restricted three-body problem provides a dynamical model for the motion of a small mass that feels the gravitational pull of two massive bodies in its proximity, but has a negligible contribution to their motion. In particular, if the Earth and Moon are considered, this dynamical model offers an adequate approximation for the motion of a spacecraft in their vicinity, a topic which has recently regained traction given the intent of returning mankind to the lunar surface. Most missions within this context target operation near the problem's 5 equilibrium Lagrange points, since it is possible to find various families of periodic solutions around them that offer a plethora of possibilities to choose from. However, these orbits are typically unstable, meaning that a slightly perturbed spacecraft will tend to depart from its target trajectory. This is especially worrisome given the chaotic nature of the dynamics, since small differences in initial conditions lead to vastly different solutions over time. To mitigate this effect, onboard actuators are introduced to the spacecraft. These are commanded by a control law that is a function of time and the spacecraft states. The objective is to design the control law in such a manner that the deviation from the target trajectory is driven to zero over time, which, in control theory, formally constitutes an orbital station-keeping problem. In literature, 2 main approaches to solve it can be found. Some authors prefer the use of classical techniques that are well-established and simpler to implement, though normally unable to account for physical constraints typical of any real mission. In contrast, other works prefer more modern alternatives that are able to include these considerations, despite usually coming at a significant cost in terms of their computational demand. In this work, these 2 contrasting approaches are bridged. Firstly, standard control techniques such as the linear quadratic regulator and nonlinear backstepping are leveraged together in the design of innovative autonomous orbital station-keeping solutions. These are established considering the 2 most common descriptions of the restricted three-body problem dynamics. That is, the simpler case, where the orbit of the Moon is taken as circular, and the more realistic case, where it is described by an ellipse. Then, similarly to more modern approaches, physical constraints are introduced to the actuators to provide further realism to the application, namely in terms of a saturation threshold to the norm of the actuation command. This consideration is included directly at the design level to ensure that the proposed control solution is still stabilizing. In turn, this novel orbital station-keeping control package is evaluated through the means of numerical trials. The results demonstrate the adequacy of the proposed solutions when targeting the most varied types of nominal trajectories, attesting to the versatility of the implementation. Furthermore, they highlight the benefits of linear optimal control when in proximity to the nominal orbit and nonlinear control when the deviation is large, which lends credence to the 2 base techniques employed in this multifaceted analysis. Finally, the validation of control with the formal inclusion of an actuation saturation threshold brings forth the strong suits of the algorithms developed, which are able to maintain guarantees for stability without a sacrifice to the computational demand of the application, representing a meaningful improvement when compared to other alternatives in literature. Ultimately, these key points highlight how the proposed solutions push beyond current orbital station-keeping strategies, putting them in line with the needs of next-generation fully autonomous missions to the Moon and beyond.